Imagine the shimmering world of metals, silver, tin, aluminum, all boasting that same classic silvery gray glow. But then copper crashes the party with a unique reddish-orange hue, and gold steals the spotlight in warm yellow radiance. Ever wondered why these two rebels stand out while the rest look the same? Let's plunge into this vibrant enigma and unravel the colorful mystery together. Okay, let's take a guess. Could it be their weight? After all, lightweight champs like aluminum and tin have that classic silvery gray look, while heavier hitters like copper and gold flaunt their vibrant hues. Seems plausible at first glance. Heavier atoms, bolder colors, right? But hold on. Silver outweighs copper by a solid margin, yet it's stubbornly gray, like it missed the memo. Lead is heavier still, and about as exciting as a rainy Monday. Platinum is one of the heavyweight kings of the periodic table, but it gleams in pure, unadulterated silver. Clearly, weight is not deciding it. Time to shrink down to the atomic scale and uncover the real quantum tricks. Let's start with the basics. Why do metals have that shiny, mirror-like look in the first place? Imagine a giant swimming pool filled with kids bouncing around on inflatable tubes. That's what a metal looks like at the electron level. The outer electrons aren't tied down to one atom. They're free to slosh around in a big communal electron sea. Now shine a flashlight at that pool. The waves of light make the kids bounce, and they throw that energy right back at you. That reflected light is what makes metal shine. A piece of wood, on the other hand, is not shiny because wood is made of molecules where electrons are locked up in strong bonds between atoms. Instead of a big pool, imagine each electron stuck in its own little private room with the door locked. When light hits wood, the electrons can't slosh back and forth freely. Instead, the energy gets absorbed and turned into heat, or scattered in random directions. That's why wood looks matte and dull instead of shiny. Same with plastic or cloth. No free electron sea, no mirror shine. And that's the key. Shininess isn't about being a solid, it's about whether your electrons are free to dance with light. Metals have the dance floor open, wood doesn't. But sometimes, certain colors of light get absorbed instead of reflected. That happens if the electrons can jump from one energy level to another, like a frog hopping to the next lily pad, but only if the color of light has exactly the right energy. For most metals, those jumps only happen with invisible ultraviolet light. That means they reflect the entire visible rainbow evenly, giving you a plain silver gray. But for copper and gold, something special happens. Copper's electrons sit just the right distance apart, so blue and green light has exactly the right energy to make them jump. Think of blue photons like the perfect coins for a vending machine. They get swallowed up. Reds and oranges are bounced back instead. And that's why copper has that warm, rosy sunset glow. If its electron levels were just a little different, it would look silver, like its neighbor zinc. Gold is copper's flashy cousin. It also absorbs some of the blue, leaving behind that golden yellow. But it's not just ordinary electron jumps at work. Gold is heavy, really heavy. Its inner electrons are whipping around at speeds close to 60% the speed of light. And when things move that fast, Einstein's relativity changes the rules. Orbitals shrink, energy levels shift, and suddenly gold's vending machine starts taking blue-violet photons. Without relativity, gold would just look like boring old silver. So, fun fact, your gold jewelry shines yellow thanks to Einstein's physics. That's right, relativity is literally built into your wedding ring. Silver, platinum, and aluminum, on the other hand, absorb the ultraviolet outside our vision. That means they reflect all visible colors evenly, and our eyes see just silver gray. So these metals wear the standard silver suit. Now, quick thought experiment. We've been saying that metals shine because free electrons bounce light back. But hold on, sometimes those electrons absorb photons and jump up in energy. So if they're busy jumping, doesn't that mean fewer are left behind to reflect light? If we keep shining light, wouldn't the metal gradually run out of shiny electrons and start looking dim, like draining the batteries of a flashlight? Sounds almost logical, but here's why it doesn't actually happen. Electrons don't just jump up and stay gone. When one absorbs a photon, it gets excited to a higher energy state, but only for billions of a second or less. Then it almost immediately falls back down, giving that energy back to the system by either releasing another photon or sharing it with the sea of electrons around it. It's like a kid on a trampoline. Bounce up, come right back down. Bounce again. The trampoline doesn't run out of kids. So the metal never uses up its electrons. The pool of free electrons is always there, instantly ready to keep bouncing light. And that's why a gold ring stays shiny year after year under sunlight instead of dimming away.
Still, not all metal colors come from electron jumps, though. Silver in its pure form is an almost perfect reflector of visible light. That's why a freshly polished silver spoon or mirror shines bright white, almost like a tiny flashlight. But leave it out in the air for a while, and it begins to darken. What's happening here? It isn't rust, that's iron's problem. Silver instead reacts with trace sulfur compounds in the air, like hydrogen sulfide. These can come from pollution, volcanic gases, or even tiny amounts released by foods such as eggs and onions. When sulfur meets silver, it forms silver sulfide, a thin, dark coating on the surface. This tarnish is one of the reasons silver has historically been seen as a little less noble than gold. Gold hardly reacts with anything at all. That resistance to tarnish is part of what makes gold not only beautiful, but also prestigious and durable. Now here's the fun part. The tarnish layer isn't just a flat paint job. When light hits tarnished silver, some reflects off the sulfide layer on top, while some penetrates through and bounces off the shiny silver underneath. The two reflections overlap and interfere, like ripples in a pond colliding. Depending on the layer's thickness, certain wavelengths get canceled while others get reinforced. If the sulfide film is as thin as tens of nanometers, it tends to cancel out blue light, leaving a warmer, yellowish tint, which is why slightly tarnished silver looks slightly golden. As the layer thickens, more of the spectrum gets scrambled, and the metal darkens toward brown, purple, and eventually flat black. Such thin film interference effect also makes soap bubbles, oil slicks, and butterfly wings shimmer. Except here, the film is a chemical crust of silver sulfide. So silver's loss of luster isn't because its free electrons stopped working. They're still shining below. It's just that the new top coat of sulfide hijacks the light show, filtering and interfering with what we see. That's why polishing silver doesn't just make it shinier. It literally scrapes off that nanoscale film, restoring the raw reflective surface beneath. So there you have it. Most metals are silver gray because they reflect all colors. Copper absorbs blue and thus looks red-orange. Gold absorbs blue plus violet and thanks to relativity looks yellow. Next time you see a gold ring or a copper wire, remember, you're looking at a quirk of quantum physics with a dash of Einstein. If you enjoyed this dive into atomic fashion, hit like, subscribe, and tell me in the comments, which metal do you think deserves more attention? See you next time.